Hello everyone, my name is DongHeun Han. I'm a PhD candidate at the IIIXL Lab. Today I will present a review of the paper titled Synthesizing Physical Character Scene Interactions by Hassan et al., which was presented at the SIGGRAPH 2023. This paper is about training physical animated characters interacting with objects. In this video, you can see characters sitting, lying down, and moving objects. All of this is done using a physics engine that applies torque to the joint of the character, and it is called physical animation. There are two main ways to create character animations. One is kinematic animation and the other one is physical animation. Kinematic animation is what you usually see in videos and games. It doesn't use physics. You just set the position or rotation of the joint and the character takes the pose. This method is clear and straightforward, but it can cause issues like foot sliding or object penetration. It can also result in poses like that aren't physically possible. Physical animation, however, uses a physics engine to avoid that problems. The characters are connected with physical joints and move with torques just like in the real world. Movement depends on the torques applied at each joint at each moment. For example, to stay standing, a character needs to apply the right amount of torque to keep from falling, just like a human uses muscles to stay balanced. Physical animation has several advantages. It's more realistic because it prevents object penetration and impossible poses. And it is robust because the character has to overcome various forces while moving. Physical animation offers several advantages including physical flexibility, eliminating object penetration, and impossible poses. The model of this paper has the following structure. The policy trained through reinforcement learning. It takes stage for input and output joint torques at each time step. The motion discriminator is a function similar to a gain discriminator. It distinguishes between motions generated by the policy and those in a human motion dataset. In this case, the policy acts like a generator, creating natural human-like movement. The policy is trained by reinforcement learning with the following reward function. Reward G stands for goal reward. It indicates task performance such as sitting, lying down, carrying task. Each task has a specific reward function and the policy learns one task at a time. Reward S stands for style reward. It indicates the naturalness of the generated motion based on how well the policy deceived the motion discriminator. The total reward is the sum of these two reward terms. The objective of reinforcement learning is to maximize this reward. Therefore, the policy leads to generating natural motion while accomplishing the task. The motion discriminator is trained like a gain discriminator. It distinguishes between samples from the human dataset and the policy. They also use gradient penalties to stabilize training. This setup follows a typical gain-loss function structure. The adversarial network structure introduced by Gale and the way it applied to physical animation field by AMP is used here. The model inputs include basic information about the character's joints and endpoint positions. The endpoint includes feet and hands, so this information can be useful for walking or interacting with objects. And it also includes the position and orientation of the target object. This means that the model can handle only one object at a time. The action generated by the policy specifies joint target rotations for PD controllers. The model architecture is very simple. Both the policy and the motion discriminator have 3 small hidden layers. Large capacity networks are rare in reinforcement learning field, since most problems can be solved with these compact structures. This paper focuses on one trivial task per policy and provides specific object information, so highly complicated network is not needed. To train the discriminator for natural motion, they use the human motion dataset. The SAMP dataset consists of 100 minutes of motion captured clips. They use SAMP for sit and lie down tasks. SAMP originally provided 7 different objects, but the authors extended this by using 350 different objects from the ShapeNet dataset. For the carrying task, they captured their own motion capture dataset. To increase object diversity, objects were randomly scaled between 0.8 to 1.2 during training, and the box object for the carrying task was scaled from 0.5 to 1.5. During training, 3 main methods were applied. First, reference state initialization is a method of starting training by sampling from a reference motion dataset. For the sit task, it could start from the middle of the sitting down motion, and for the carrying task, it could start while holding the object. This skips the sequential learning process of approaching and picking up the object, allowing direct learning from the key action. Next, early termination ends the training early if the character falls or can't recover. Characters often fall a lot in early training, so early termination prevents wasting time on learning to stand up before learning to walk properly. In this paper, early termination is applied if hands or feet get within 20 cm of the ground or the box gets within 30 cm of the ground. Lastly, randomization is the data augmentation method proposed by the authors. It increases scenario diversity by randomly initialize the position and orientation of the object and the character at the start of training. This allows the character to perform the target task from any position or angle. The results are shown as well. The results show that the character performs all 3 given tasks well. It can sit, lie down, and carry a box with its hands. Also, the character performs well with unseen objects during the training process. Also, you can see the effect of randomization. The character adapts to randomized target in real time. You can see the advantage of physical animated characters. Most of the physical animated characters can robustly perform even with the physical perturbations. For evaluation, they conducted quantitative evaluation. The success rates were defined for each task. For the sit task, success was achieved if the hip was within 20 cm of the target. For lie down task, success was achieved if both the hip and head were within 30 cm of the target. For the carry task, the box had to be within 20 cm of the target. If the task was not completed within 20 seconds, it was considered a failure. They also varied the weight in the carry task. As you can see in the table, the quantitative results for each task show a success rate of over 90%. Even with physical perturbation, success rates were above 80%. The paper mentions they can perform many scenarios with a small dataset. As shown in the figure, the reference dataset contains only a few trajectory scenarios, but through randomization, it performs well in many unseen scenarios. However, this is likely because the Gale method with a discriminator does not rely on one-to-one comparison with specific data. And even though randomization was applied, randomization is a very basic form of data augmentation. Therefore, in my opinion, covering many scenarios with a small dataset cannot be considered a significant contribution of this paper. Also, they conducted a comparative analysis as well. They implemented kinematic-based methods such as NSM and SAMP, as well as the physical-based method by Chow. The table shows that all these methods have a lower success rate compared to this paper. The physical-based method by Chow has so many failures that some matrices were not possible to be measured. Also, the kinematic-based method showed issues like object penetration and foot sliding, indicating their physical plausibility problem. In conclusion, this paper is notable for integrating existing methods effectively into scene interaction tasks. However, there is nothing particularly new about the proposed approach. The introduction of the motion discriminator and the use of randomization are already known. However, the authors combined these elements to tackle the new problem of scene interaction tasks with physical characters. The another problem is evaluation methods. Since the model is trained to perform only one specific task, it's not surprising that it succeeds. Also, the comparative evaluation isn't perfectly fair, as pre-trained models for each method were used. Lastly, the authors claim it's an advantage that their agent automatically accomplish the task, unlike kinematic-based method that needs user control. However, providing user controllability is much harder and encourages a wider range of behaviors. The lack of controllability actually could be a limitation of this paper. In summary, I'd like to suggest some future improvements before we end the presentation. 1. Developing more controllable model for trajectory control and the selection of target objects. 2. Creating a universal policy that supports multitasking. 3. Addressing more complex tasks such as long-term operation. 4. Enabling tasks that require 2 or more actions simultaneously. Last, handling objects with the same purpose but extremely different shapes. Thank you for listening. This is the end of my presentation. If you have any questions, please leave them in the comments.